Okay. So first thing you did should have been to subtract the 22 from both sides, right? Okay. And then we're going to do the exponent 3 over 2 to both sides to cancel the exponent, right? Okay. And because that's an even root, because the denominator on the exponent's even, I get the plus or minus. And then I'll subtract the 43 and divide by 3. Oh, that's even better. Thanks. Yeah, I love that. So that's that. And then all I have to do is worry about 16 to the 3 halves. So notice that 16 is 2 to the 4th. So that's really just simplifies down to 2 to the 6th, or 64. Is that okay, Mackenzie? So 16 is 2 to the 4th, right? And if I have an exponent to an exponent, I multiply the exponents. So that gives me 2 to the 6th, which is just 64. So I have this. So 64, or negative 43 plus 64 is 21. Divided by 3, that's 7. And then negative 43 minus 64 is negative 107 divided by 3. That doesn't reduce. So there's that. And since that's an odd root, we shouldn't need to check those. Is that okay? Who's next? Alyssa.
7 on the same worksheet.
7 from the same worksheet. Okay. So I'm going to start by adding the 8 to both sides and then multiplying by negative 4 to get rid of that fraction. Is that okay? I'm going to do that all in one step. So 12 times negative 4 is negative 48. Is it okay for a cube root to equal a negative? You betcha it is. No issues there. So I'll just keep on going. So we'll cube both sides. Yucky McYuckerson, what is that going to turn into? Some big honking number, huh? Let me pull out the old calcutron. 48 to the 3rd power is, oh my gosh, 110,592. So I'll subtract 10 then. And then multiply by 4/3. You would, you stupid machine. Why wouldn't you give me that as a fraction? Grr. So I have x equals 442,328 divided by 3. Girl Google. And again, since it's an odd root, don't have to worry about checking. Is that okay, Al?
Yep.
Cool. Others. Happy to do more if we need to do some more. Again, these problems I don't think are the most difficult thing we've done in this chapter, but there's some tricky ones in here for sure. Right? Definitely some places we got to be careful. Happy to do more if you got more to ask about. If you don't, that's fine. We can always come back and talk some more later. It's no big deal. Mac. 12? Sure. I'm going to go take that work and do it down here, though. Did I copy that correctly? Okay. So first thing I'm going to do is divide by 9. And then to cancel that 2/5 power, I'm going to use the 5/2 power. And really, in place of 4, I'm going to write that as the prime factorization, which is 2 squared. Exponent of an exponent. Whoa! Hold on. What did I forget? Plus or minus. It's almost a disaster there. Exponent of an exponent means I multiply. So I have plus or minus 2 to the 5th, or plus or minus 32. And again, that's an odd root, right? Because the denominator.
Why is it plus or minus?
So when I did this to the both sides, because the denominator is even, it's really like doing a square root or an even root.
Okay.
That's where the plus.
Now.
Yeah, Emily, come on down.
Bring your stuff out.
Oh, never mind. Keep moving. Is that okay, Maddie, with what we said?
Well, I'm sorry, what'd you say?
So since that is an even number, it's like doing an even root. In this case, it's like the square root of both sides.
Mm-hmm.
So that's why we're getting the plus or minus, because we square rooted both sides of the equation.
Okay.
Just like if we're solving a quadratic, we get a plus or minus. Same idea. Mackenzie, are you happy on that? Okay. Did you do it right?
I got to the 45.
Oh, you didn't keep simplifying? Well, you had the right answer, you just didn't have the fully simplified version. Which is important, but like not the most important thing. Like getting, having the right answer matters too. You know what I mean? It's not like you were wrong, you just stopped too soon. Which is not the end of the world, right? Eventually people stop caring about what your answer looks like and are just like, dude, an answer is the answer. But we have to care now so that we know that you can convert things or whatever. Maddie, do you have a question? I couldn't tell if that was a hand coming up or not.
Can you do number 25?
Yeah, can you just tell me the problem here? I don't think I'm going to have space.
3 cube of 2x minus 5.
3 cube of
12x minus 5.
Okay, the cube root of 12x minus 5. Thank you.
Minus the cube root of 8x plus 15 equals 0.
Okay. So my first step is to isolate one of the radicals. To do that, I'm just going to add the cube root of 8x plus 15 to both sides to move it onto the other side. That step makes life tremendously easier. So when I cube both sides, the cube roots just cancel out in both locations. Whoa! And now it's just like a linear equation here, right? So I subtract 8x from both sides to get 4x. add 5 to both sides to get 20, and divide by both sides by 4 to get 5.
Okay.
And since they're odd roots, you don't need to check it. Had you started by cubing both sides of the equation, you would have made yourself a gigantic mess, because you would have had to FOIL that thing out, which is not going to be fun.
Then checking it, just putting it, plugging it, right?
Mm-hmm. But it's an odd root, so you don't have to check.
Okay.
It'll work. Edmund.
Can you explain once again what you did between the first and second steps?
I just added this cube root of 8x plus 15 to both sides, just to get it on, so I have one of the radicals isolated. In fact, I isolated both the radicals that way, which is like the best case scenario when you have two separate radicals. Because when you're able to do that, then they just go, both of them go bye-bye. And that's not so bad.
When you plug it in, do you have to plug it into like
The very beginning.
The cube root?
The very beginning.
Okay.
Everything going on. The very beginning is where it gets plugged into, with everything still there. And it has to work. So any intermediate step you plug into, not sufficient. Gotta be the original problem with all the roots and everything still in there. Because that's the thing that's going to cause the extraneous, is you're going to end up with a negative sign under an even root. Or possibly two things that just don't add up right after they come out of a root. But you need the roots there for the check to work. Let's do another. Do you guys want to do some more? I'm happy to do some more. If you don't want to do them, though, that's cool too. Like, I'm not trying to peer pressure you or anything. But quite frankly, we're not peers, so.
Can you just check number 24?
I mean, I don't know what the answer is off the top of my head. Oh, I can do that in my head. It's going to be 3. That one I could do in my head. I lied to you. Is that what you got?
Yeah, that's what I got.
Well, that's good. Did you check it?
Yeah, no, that's why I was like, I want to make sure I checked it.
Because it should have. You should have gotten cube root 13 equals cube, or square root 13 equals square root 13.
Okay.
When you checked that, so it should have worked. Okay. Any other takers? Okay. Well, it's not the end, right? You can still ask questions later if you want about this. You know, there's no reason we can't come back and revisit. There were some tricky sons of guns on here, so don't feel bad if you're like, yeah, I need to come back and ask about this one here because I got lost in the weeds or whatever doing it. I know that not all of us have finished all the homeworks yet, and that's fine. Okay, so we've done simplifying, we've done graphing, we've done solving. What I want to circle back to is this idea of an inverse function. So we did this a bit already in first semester if you were in my crew. If you had Miss Morgan, I'm not sure if she did this in first semester or not. So we'll just kind of do it a little bit here also and talk a bit about inverses and whatnot. This is a natural place to do it since this is these radical functions are natural inverses to a lot of polynomial functions. So let's just remember what we meant by a function. So we say that a function is a set of ordered pairs where every element in the domain is paired with exactly one element in the range. So again, that's just a refresh from first semester where we talked, really we spent a good bit of time here at the beginning of the semester talking about functions. At least my crew did. I'm not positive how Miss Morgan started the year, but I think you guys talked about this stuff too. So we had a couple of different ways you could represent a function. So you could represent it naively with like a set of ordered pairs. So we know that this set of ordered pairs represents a function because if I look at the domains, that's the values for x, those are all unique. That's all we need, right? Cool with that? Okay. We also sometimes represented our function with a mapping diagram. Where we used an arrow to indicate the values that are paired together. Which again, this is representing a function because everything in our domain goes just one location. Doesn't matter that some of them go to the same location, they just have to go one place. Everybody's okay with that? Another way we represented a function was with like a graph. So if here's my xy axis, if we had something like this, this represents a function because there's no x coordinates that are used more than once. And I know that because any vertical line I draw would only intersect the graph in one location. Right? That was we called that the vertical line test. It's okay there? You guys remember that? If I do anything that you're not remembering, holler at me and we can talk some more about it or whatever. And then the last way we had to represent a function would be with an equation. And we could use, oftentimes we'll use y equals or we'll use f of x equals. It doesn't really matter. They basically just the different notations to represent the same idea. And I know this is a function because if I look at 3x squared plus 7x minus 2, that thing is quadratic, right? And all quadratics are functions, so. Because I know the graph is going to look like a U, which would pass a vertical line test, right? One way to think about a function is like a map in the domain. I apply a function to it, and it turns into something in the range, right? And now a natural thing that you want to do is to be able to undo what you just did. So we'd like a function. Let's color code this. Whose domain was the outputs for our function f, and whose range would be the inputs. It's basically just undoes whatever f did, right? Right, take the outputs of f, and I do a new function on them, and it gives me the same value back again. We call a function like this the inverse of, and oftentimes we'll use the notation then f inverse to represent it. Okay. So if I have my function that is represented by the set of ordered pairs, and I want the inverse of that function, what do I need here? Well, let's think about it for a second. A mapping diagram, maybe rather than a set of ordered pairs. So if I have the point 3, 5, the point -2, 10, and I have the point 5, 3, and then we have the point 6, 5. Okay. Or that's our f of x. So if we wanted the inverse, the domain for our inverse is going to be the same as the range. And the range for our inverse should be the same as the domain for f, since it's just trying to like reverse the direct. But it should also go to 6, 2, and 3 should go to 5. So this could be what we call f inverse. But what do you notice about f inverse? What's about f inverse? Not a function. Okay. So sometimes the inverse will be a function, but sometimes it won't be. So just there's, I'd have the point 5, 3. I'd have the point 10, -2. I'd have the point 5, 6. Notice what we did there is we just swapped the x and y coordinates, right? So far, so good. Coolsville daddy-os. Okay. So how would I know if a function's inverse is still a function? This will be a function. I can tell at f of x. So to determine if f inverse is going to be a function or not, we can just look at our function for f of x. We know that f of x has, if it has any repeated y coordinates, then f inverse will not be a function. Otherwise, f inverse would be a function. We say that f of x is 1-to-1 y coordinates. So another way to phrase that statement is, if f of x is 1-to-1, then f inverse would be a function. Everybody okay so far? Okay. So let's consider this negative 2x squared. If I look at the graph of this, it's going to look kind of like this. Everybody okay there? You guys agree? I know the parabola opens down because the leading coefficient is negative. And I know because there is no regular x term, the vertex of the parabola is going to lie on the y-axis. In this case, at the y-intercept, 0, 3. Right? If you weren't sure, you could always type this in your calculator and look at the picture, though, right? But not unreasonable to expect that you'd be able to look at that equation and be like, give me about what the picture would look like. Now, in this case, f inverse would not be a function, right? Because almost all of the y coordinates are used twice. For example, y equals 1 is used 2 times. Right? This is the point 1, 1. This is the point negative 1, 1. So suppose we want to find an inverse for f of x, but we want to somehow make our inverse into a function. Not an unreasonable thing to do. We'd prefer to work with functions than not, because we like things that have a causal relationship. Like if I give you x, I get exactly one thing back, not like, oh, you could get these 8 things. Which one am I going to get when I plug it in? Oh, I don't know. Right? That's not a very satisfying function. We like to have a little bit of determinism in there, where if I give you one thing, I know exactly what I'm going to get back, not like, I don't know, there's some choices. It's going to be one of these. I can't tell you more than that. Not very satisfying. So what we'll do is we'll basically truncate our function f of x to get rid of any repeated x's. So I could take just, say, the right half of it. By taking the x's that are greater than or equal to 0 and only considering that function. Again, f of x is still a function. I've chopped off the piece of it that makes it not 1-to-1. Now that I've done that, I could create an inverse from this. So there's kind of two ways that we might represent our inverse in this situation. I could create the graph, or I could create the inverse using an equation. If I'm going to be looking at the graph, what I'm going to do is I'm going to imagine the line y equals x. So the coordinates on the line y equal x are like 1, 1, 2, 2, 3, 3, 4, 4, -1, -1, -2, -2, etc. Everybody's okay with that? And I'm going to reflect my graph across that line y equals x. So when I do that, this point 0, 3 becomes the point 3, 0. This point over here, which was square root 3 over 2, comma 0, moves over to here. And like this tail down here kind of moves up here. So what I have is something like this. Is that okay? Not very satisfying though. Typically, if we want a function, we're not really interested in what the graph looks like. More so what we'd be interested in is the equation. So the way we did that is we would replace the f of x with a y, and then we would solve this for x. So I'll subtract 3 over from both sides. Divide both sides by -2. So here I'm going to push the negative sign into the numerator, which is going to make the 3 positive and the y negative. Just to make it a little bit cleaner. We typically don't write a negative sign in the denominator of a fraction. That's kind of the standard. Wouldn't be wrong if you left it there, but I don't like to do that. I like being prim and proper. No? I thought it was going to be, I thought that was a funny voice, but nobody thought so, so that's okay. And then we'll square root both sides. Remember, when we square root both sides of an equation, though, that's going to create a plus or minus, which is what's causing the thing, if we were to find our inverse, to not be a function. This is the point, though, where this restriction is going to come into play. So I know that x is greater than or equal to 0. So here I have x equals plus or minus this. The stuff coming out of a square root can only be positive. So what I can do is drop the negative sign there. Since x must be greater than or equal to 0, and then my final step would be to swap the x and y coordinates. and I can call this guy my inverse. You want to do another one? It's up to you guys, man. I'm cool either way. Totally coolsville, dude. You just need a minute to process. I can slow down and give you a minute to kind of process. I don't know. You guys tell me. You know, I already know how to do it. I just want to give you guys the roadmap to success here, so to speak. Okay, you're being so communicative. It's very helpful. Let's do one more. You ready for a toughie? Yeah! Your enthusiasm is delightful. Oh. All right. So first thing I would do is I'm going to sketch a little picture of this. So I think it's going to look something like this. You could always do that part on your calculator to just give you an idea. So what I'm going to do is I'm going to take this piece is what I'm going to cut off, or I'm going to only consider that part of it. Everybody's okay with that? So what I need to do is, before I get going, is to figure out what that x coordinate is, right? Well, that point that I'm pointing at has a special name. What's that point called? Oh, the vertex, right? Everybody remember that? Do you remember how to find the vertex for a quadratic in standard form? Oops, let's write that as f(x). So our quadratic, the vertex is always going to be found by negative b over 2a, comma, f of negative b over 2a. Now, I don't give two poops about what the y-coordinate is. Not interested. It's the x-coordinate that I am interested in. So here I notice that a is 2, b is negative 3, and c is 4. So the x-coordinate for my vertex is 3/4. So the restriction I'm going to place is that x has to be greater than or equal to 3/4. Is going to be what I'm going to be cutting. Sound good? Hopefully all that looks a little bit familiar at least. We did it all this year. It's just been a little bit, so I'm not surprised if you're like, I don't remember that. It's okay. You should at least be like, oh, that looks familiar. I'll settle for that. Remembering would be better, but at least recognition going, yeah, okay, that was a thing we did. I'll settle for, you know. It is Friday, 2 days before spring break, so cut you a little bit of slack on that. So now we're ready to go. We have this. We're ready to start finding our inverse. To find the inverse, we need to solve this for x. What's going to be the best way to do, or let's rephrase, what's going to be the fastest way to do that? Oh, guys, here's what I'm going to do. I'm going to subtract y from both sides so that it's equal to 0. There's your hint. Now what do you want to do? You have a quadratic equation that's equal to 0. Then I'm asking you to solve for x. The quadratic formula. Yeah. So in this case, a is 2, b is -3, but c is 4 minus y. Isn't that so much nicer than like trying to do completing the square or some other nonsense? Which you could do. I don't want to do that. I'd rather just take advantage of the nice quadratic formula there. So I could simplify things down there a little bit. Negative of -3 is +3. Then I have 9 minus 32 plus 8y all over 4. And I guess let's clean up the stuff inside there a little bit. I'll write that as 8y minus 23. Okay with that? Here's the yuckos, though. Still got that plus or minus. Here's the catch. I'm going to think about that as 3/4 plus or minus 8y minus 23 over 4. Again, I know anything coming out of a square root must be positive. And I know that x has to be greater than or equal to 3/4. That's what we spent the beginning of this problem doing. So what can that allow me to do? Drop the minus from the plus or minus. Oh, that's nice. And then I'll just swap my x's and y's. I'm going to rewrite that all as and I did a bad job here. Should look like that. And that should be my x. Come on, Kulik. So I would say then f inverse of x is equal to 3 plus root 8x minus 23 all over 4. Shaboom! Just to kind of illustrate what's going on. Actually, I'm not going to use that one. I want to use this one. Bless you. You're welcome. I'm going to use this grapher just because it's easier to do a restricted domain on it. So just to give you a pictorial or graphical view of what we just did. So there's my function, right? So I think I used those. Domain entered could not be parsed or did not evaluate. Is that what you're arguing with me about? No. Your equation and try again. Oh, maybe I need to forget how to do this. I'll just try that. There we go. Okay, so then I cut off half of it. I'm left with just this piece, right? Everybody's okay? Now to find the inverse of that, I'm basically going to be reflecting across this line y equals x. So this is like my axis of reflection. So that was y equals 3 plus square root 8y minus 23 all over 4. Oh, stupid x. There we go. Is everybody okay with graphically what we did? So this is our original function after we truncated its domain. And this is my resulting one where I've reflected it across that line, right? Everything looks like it matches up that way. So just to give you a pictorial of what it is that we did, because sometimes it's nice to think about it in more than one form, right? How you guys feel on this? Yes? Of course. You guys that came from Miss Morgan, do you guys remember doing this first semester? Did you do this already? Did you do the restricted domain stuff? Okay. I just want to make sure we're doing at least a little bit of something that's new. I don't think we did much restricted domain stuff first semester. I might have mentioned it, but I don't think we spent really any considerable time on it, right? Since we didn't know how to find the vertex of a parabola, it wouldn't have made sense to do it at that point. But we can do that now. Okay, cool. I'm glad that worked and gave us a nice picture. Right? So the other thing that we might like to be able to do is to prove two functions are inverses. So for this, we have a theorem. We say that excuse me. So the theorem that we have to answer this question states that f and g are inverses if and only if That's what the IFF is an abbreviation for. F compose g of x is equal to g compose f of x, and both of those come out to be x. So let's just kind of demonstrate that using our two functions we just created, because these are, I think, adequately complicated to make this not trivial. So we know these two things are inverses, right? We just made them to be inverses. So we know that when we do these two compositions, we better darn be sure getting x. But the algebra there might not be trivial to do that, because these are rather complicated functions that we have. They're not just like two linear functions. It would be, not so bad. All right. So let's start by doing the first composition, f of g of x. So to do that, I'm going to replace my g of x, what that's equal to. And now I'm going to be plugging that in x's in my f of x. Algebra 2. All right. So I'm going to begin by foiling here because of the squared. Are you guys game to let me just foil that out in my head, or do you guys need to see it? Please say you're good. Okay, I saw one thumb, I'll take in it. So that's going to be 9 plus 6 root 8x3 plus 8x minus 23. And then I'm going to go ahead and distribute my 3 through. Actually, let's do this and distribute a negative 3 through. That'll probably be easier to keep track of the negatives if I do it now, right? So I'll reduce there. Cool. And then make a denominator by multiplying this guy by 2 over 2. And this guy by 8 over 8. Is that cool with everybody? So let's see, I have 23 plus 23 minus 18 minus 6 root 8x minus 23. Plus 32 all over 8. Let's see now. So I have a positive